Well, so last time we did the theory of duality for linear programming. And this lecture is going to be devoted to the practice of duality in linear programming. We're going to learn some cookbook methods, and we're going to look at actually various applications of taking duals and how that works out. Sorry, I forgot to put those. So duality in practice. Now, in practice is, of course, a relative term. This is still a theory course, but we're going to be looking at least at rules for taking duals. So what we saw when we did the theory of duality was I showed you how you could take a linear program in standard form and how you would take it, you would construct a dual, which would be in canonical form, and then I proved strong duality so that the value of that canonical form dual linear program is the same as the value of the standard form primal linear program. Okay? And from a theoretical perspective, that is enough because we know that any linear program can be transformed into standard form. And so you could always do that. You could transform to standard form and then get the canonical dual and be done. But that's a lot of work and creates a lot of mess. So what we're going to now talk about is how you take the dual of any linear program without having to make that transformation. Okay? Boy, the distribution of people in this class is very interesting. We've got like this full row when you've got this entire amphitheater for that you could occupy. It must be a fraternity or something, right? Everybody hanging out together. So let's talk about a general linear program. So if you think about a general linear program, you'll have some objective function, which we might as well take to be a minimization objective. And what I'm going to do is I'm going to consider three different kinds of variables that may show up in this linear program. The differences have to do with whether the variables are constrained to be non-negative, like they are in a standard form LP, or whether they're unconstrained, or we'll also allow them to be constrained to be non-positive, because that will turn out to be relevant. And then you have a bunch of constraints. And again, I'm going to break out according to these three different types of variables. And I may have some equality constraints. Now, I might also have some lower bound constraints. And I may also have some upper bound constraints. And then, as I said, we have these three different kinds of variables, some of which are constrained to be non-positive, non-negative, some of which are constrained to be non-positive, and some are unrestricted. So UIS stands for unrestricted in sign. Okay? So this is the most general form of a linear program, right? A combination, a linear objective, a combination of upper bounds, lower bounds, and equality constraints, and a bunch of, and variables which can be constrained to be non-negative, non-positive, or unconstrained. Okay? These may seem a little odd, but we've seen in the standard form linear program these greater than or equal to 0 constraints. And so it turns out that it's natural to consider them. So if you have that sort of linear program, and you take its dual, you always get a maximization problem as a dual to a minimization problem. And I am again going to break out the variables of the dual as positive, as non-positive, non-negative, and unrestricted. And as we've seen, right, if the primal has these vectors right multiplying the constraint matrix, then the dual has the vectors left multiplying the constraint matrix, right? So we work with rows instead of columns. And so the matrix basically transposes. So now we say that y1 times a11 plus y2 times a21 plus y3 times a31. Sorry, the colleague that I co-lectured with last time went and transposed all the matrices in my notes. And so I'm trying to untranspose them in my head. So hopefully this will work. Whoops, C1. So there we have our upper bounds. We have sorry, y1, a12, y2, a22, plus y3, a32, greater than or equal to C2, and again, just like on the primal side, we have some variables that are unrestricted. We have some variables that are required to be non-negative, and some variables that are required to be non-positive. Okay? Now, remember that our matrix was a matrix of constraints by variables, right? So in the primal, each row was a constraint, right? And each column corresponded to a variable, right? When we take the dual, it switches, and now each row corresponds to a variable, and each column corresponds to a constraint. So what that tells you is that for each variable in the primal, you get a constraint in the dual. And for each constraint in the dual, you get a variable. For each constraint in the primal, you get a variable in the dual. Yes? That just comes from the shape of the matrix and the transposition that you're performing. All right? So that's a kind of a notation-heavy way to write this dualization process. And I've just defined the dual. But if you think about the process by which I derived the dual in standard form, where I talked about coming up with a lower bound for the value of the objective function and taking linear combinations of the constraints, right, to find the best possible lower bound, right? If you generalize that argument, then you do derive this shape for the dual of the linear program, and you will be doing that on your problem set, right, to sort of get this more general derivation of a dual. As it's written, it's a little bit notation heavy. So here is something that's kind of nicer for the cookbook. So what we do is we talk about this primal linear program. And the primal is always going to be, for simplicity, a minimization problem. And it is going to correspond to a dual, which will always be a maximization problem. And again, which one you call the primal and which one you call the dual is really arbitrary, since these things are symmetric. All right? And what we've just seen in our derivation is that we've got different kinds of constraints in the primal, right? We have some constraints that you should be greater than or equal to. We've got line too close. We have constraints that you should be greater than or equal to a bound. We have constraints that you should be less than or equal to a bound. Or we have constraints that you should be equal to a bound, right? And this primal linear program will also have variables which are constrained to be non-negative or non-positive or unrestricted. And if we now look at the matrices that I drew above, we see how these get transformed, right? So every constraint in the primal corresponds to a variable in the dual. Every variable in the primal corresponds to a constraint in the dual. Okay. Now, the next thing that we recognize is the relationship between the types of variables. So again, a standard form linear program, right, has these equality constraints in it, and those correspond to unrestricted variables in the dual, right? If you remember the canonical form LP, the variables are not restricted, right? Conversely, the canonical form LP, right, which was a maximization problem, which then had constraints that certain things be less than or equal to a certain quantity. Those constraints in the canonical form LP corresponded to the non-negative variables in the primal LP. So we get upper bound constraints corresponding to non-negative variables. We get lower bound constraints corresponding to whoops, did I get that backwards? Yes, sorry. No, that's right. Lower bound constraints corresponding to non-positive variables, and unrestricted variables corresponding to equality constraints. And similarly in the other direction. Okay, so this is the complete cookbook for taking a dual. Okay, so I mean, you still have to do the work of looking at the matrix and figuring out how to write constraints that correspond to columns now instead of constraints that correspond to rows. But this tells you about the direction of the inequalities. Okay, and it makes sense once you've thought about it for a little while, right? So, as we saw in our, sorry, a question?
Why is it that in variables, so like the greater than or equal became less than or equal to, less than or equal to?
Yes, let me explain that right now. So we saw in our physics intuition for duality that the dual variables represented force magnitudes, right? That were sort of how hard were the constraints pushing on the point, on the optimum point, or on the ball at the optimum point, right? And so the physics that we looked at said, well, when you have a minimization problem, right, but you have lower bound constraints that are right, the ball is trying to go down, but the constraints are trying to hold it up, then the magnitudes of those forces are non-negative, right? They're pushing, not pulling, okay? So in a sense, right, if you have a minimization objective, then lower bounds are kind of the natural direction of a constraint that's trying to keep something from minimizing. And therefore, it's natural that the force exerted by that constraint be positive. However, if you turn the constraint upside down, you turn it into an upper bound constraint, then you also invert the direction of the force. And so now the force is going to be negative in magnitude instead of positive to make up for the inversion of the constraint. So that's why you get a non-positive variable here, right? And finally, if you are stuck in the constraint, then it can go in either direction. right? If you're forced to be in the hyperplane, then you're sort of constrained from going up or down. And that's why the force could go in either direction, depending which one is needed to keep you where you are. Okay? And the story for the primal variables is the same, right? That a positive force, a positive variable, that corresponds to constraints that are in the natural direction, right? If you have a maximization problem in the dual, right, then you would expect upper bound constraints. And so those are the constraints. Upper bounds are what you see with the non-negative variables. Conversely, if you flip it and you want to make lower bound constraints on a maximization problem, then you also flip the direction of the forces. And the same argument that equality constraints correspond to unrestricted in sign. Yes?
I guess this is kind of more of a general question. Why do we care about like both greater than and less than constraints, at least in the first part, because we can just...
Yes, so this is kind of the point. As I said at the beginning, we don't need any of this because we can always convert a linear program to standard form, right? We add variables, we flip signs around, we split variables into positive and negative parts, right? That all works in theory, but in practice, it just makes your linear program much messier. Right? Somebody presents you with a simple, elegant linear program. By the time you're done with all of these transformations, you've got 3 times as many variables, and it's just a mess. So this is just here to skip all of that mess of transforming linear programs. And so for the same reason, if you're given a linear program where the constraints are in this form, this saves you the hassle of transforming that linear program. And you can just dualize it directly. OK? Yes?
Could you explain how to use the main and the max column of the table?
Oh, this is simply saying that just in order to pin things down, right? I mean, a linear program can be a minimization problem or a maximization problem. I am simply saying that whatever the, and when you take the dual, it flips, right? So I'm just calling the minimization problem the primal one here, and the maximization problem the dual one, right? So this is a linear program for which there is a minimization objective, and this is the dual linear program for which there is a maximization objective.
So for example, in the main column, there's something like greater or equal than D1, what does that mean?
Right. So in this column, this is saying, right, this is the objective description. These are the constraints. So any constraint on the linear program can be a lower bound constraint or an upper bound constraint or an equality constraint. And this is simply saying that when you have a minimization problem, then the lower bound constraints get dualized into non-negative variables. On the other hand, if you have a maximization problem, then the lower bound constraints get dualized into non-positive variables.
So in the example above, you have, say,
Okay.
something.
Yeah. So this is a direct mapping, right? So what I've drawn as the primal is the minimization problem. Oh, I'm sorry. I guess I changed the subscripts, right? So up there I used B1 for the equality, and down here I'm using B3 for the equalities.
So you have something greater or equal than E2. That should dualize into something like greater or equal to 0, right?
That's right. If I have a greater than or equal constraint in the table, if my constraint has to be greater than or equal to something, then the dual variable is going to be constrained to be non-negative.
So how does that manifest in the right side?
Well, again, if you go the other way, it's the other way around, right? If you start with a maximization problem, and I have a constraint that something has to be greater than or equal to something, greater than or equal to C2, then the dual variable for that is constrained to be non-positive.
You have greater or equal than B2 as a left side.
Yes.
So in the right side, what do you have?
Yeah, so for each constraint in the primal, you are going to create a variable in the dual. Okay, which is, again, what I did up there, right? Each row of this linear program, right? Each row of the matrix is one constraint. And in the dual, for each row of the matrix, I'm going to have one of these yi variables. And so the ith variable yi is going to correspond to the ith row, which is going to correspond to the ith constraint in the primal. Okay?
So for the YouTube example, you have y2 non-negative, right?
Yes. All right, so one other thing I'm going to point out is that when a constraint gets tighter, the dual variable gets looser. Right? So if I switch from an inequality to an equality, then I switch from a variable that is constrained in sign to a variable that is unconstrained in sign. Why does that make sense intuitively? So if I tighten the constraint in the primal, what is that going to do to the objective? Yes?
It's going to make the objective worse.
It's going to make the objective worse, which is to say bigger, right? Because this is a minimization problem. When I tighten constraints, the objective gets worse. What does that do to the dual?
The dual objective's got to get better.
Exactly. Notice that when the primal objective gets better, the dual objective, when the primal objective gets worse, that means the dual objective is getting better, right? So there's a tightening constraint in the primal makes the primal objective worse, and that corresponds to a loosening variable in the dual so that the dual objective can get better so that they can stay equal to each other. Okay? Also, in another version of this sort of things get tighter argument is, what happens when I add a constraint in the primal? I've added a constraint, so the primal gets worse. It gets bigger. What happens in the dual? I get a new variable, which gives more flexibility to the dual, so it can get better while the primal is getting worse. Okay? Let me see. Okay, let's take a dual. So let's look at the shortest path problem. So it actually may not be entirely obvious. How does one formulate shortest path as a linear program? Okay. And so I'm going to do it in the following way. I'm going to, again, physics. I'm going to take my network. I'm going to cut ropes corresponding to each edge of the network, and I'm going to tie them together at the appropriate vertices. And then in order to figure out the shortest path from S to T, I'm just going to lift up S. Okay? And the entire network will dangle down from S. And I claim that what will determine how far down T hangs is just the length of the shortest path from S to T. Right? And so what I'm applying is the perspective of shortest path that is sort of focused on the triangle inequality. Right? So if I write that down mathematically, it's actually a pretty straightforward linear program. What I'm going to say is that I want to maximize the position. We'll use these D variables to represent the heights of these vertices when I lift up the network. Right? So I just want to maximize the spacing between S and T, subject to the triangle inequalities, namely that dj minus di should be less than or equal to the cost of edge uv. Ij. for all I and j. Okay? So we're trying to spread the vertices as far apart as we can, but we're constrained by the lengths of the individual edges. Okay? So does everybody buy this as a formulation of shortest paths? All right, then. We can take the dual. So in order to take a dual, the hard part is to think about the shape of the constraint matrix. Right? So what does our constraint matrix look like? Okay. If you think about it, we have one constraint per what? Per edge. So the rows of the constraint matrix correspond to edges, right? And what do the columns of the constraint matrix correspond to? Yeah?
Nodes.
Nodes, vertices, right? So we've got a matrix of vertices by edges. And what are the entries? What do we see in a particular row? Yes?
Where does this in that edge? So one for like the if the edge is A pointing to B, then it's like one for A and direction one for B.
Exactly. We get a +1 and a -1 and a whole bunch of zeros. Right? We get a +1 where the edge, at the head of the edge, at the head of the arc, and a -1 at the tail of the arc. Okay? So what happens when we take the dual? Well, in the primal, or sorry, because this is a maximization problem, I'm going to, for consistency with the table, refer to it as the dual. So now we're going to construct the primal. Okay? So when I go from this dual to the primal, what changes? Before we had one constraint per row, one variable per column. When we go to the primal, it flips around. Now we are going to have one constraint per column and one variable per row. Okay? So this is my dual. If I look at the primal, I'm going to have a variable per edge. Right? Because before there was a row, there was a constraint per edge. Now there's a variable per edge. And I'm going to have a constraint per node. Okay. So let's call these variables y sub e. Okay. So again, that's one of the easy steps, right? I know that I'm going to have a variable for each constraint in the dual, so however I'm indexing the constraints, I'll use that to index the variables. Okay. Now, what kinds of variables are these? Right? We had these. Let's see. Do I want to do that first or the objective? Yeah. So what kinds of variables are these? Right? We've got these non-negative, non-positive. And unconstrained. What kinds of variables are we going to use in this primal? How do we figure that out? Yeah?
All our constraints are less than constraints.
Correct.
We have BJ plus CIJ.
Exactly.
So that's the dual, so then our variables will all be positive.
Exactly. We have a maximization problem. The constraints are upper bounds. and that means they're in the natural direction for the objective, and that means that the corresponding forces are non-negative. Okay. So let me move edges over here, because over here we have our variables di, right? And then we have our constraints, whatever they are. And what goes on the right-hand side? What are the bounds in our constraints? Yeah? The CIJs, right? Yes, question?
Yeah, for the original bump, do you also need to specify like ds equal to 0 and like di greater than equal to 0?
Well, that's an interesting question, right? If you look at this LP is actually shift invariant, right? If I add 17 to every variable, it doesn't change anything. Right? So there's just a degree of freedom in this linear program, and that's allowed. Right? Because notice, the objective is also shift invariant, so it doesn't matter. Now, what you're saying is, and it's true, without loss of generality, I can set ds to 0. I could add a constraint that ds is equal to 0, and it doesn't change the objective. And then I could interpret everything in terms of that the di would just be the distance of I from S. But this is a valid linear program as it stands, and it will still compute the shortest path for me. Okay? OK, so I've got these non-negative random variables. These non-negative primal variables. And now I also have these constraints on the right side. What do these constraint variables on the right side become in the dual? What do they turn into in the primal? Well, each constraint becomes a variable, but what role does Cij play? Yes? They become the coefficients of the objective function, right? So you can read off the objective function in the primal just by looking down the bounds in the dual, right? And each of these coefficients multiplies the corresponding variable in the dual, or in the primal now, right? So our objective function is just a sum of CE times YE, right? Now, is it a minimization or a maximization? It's a minimization because the dual was a maximization, right? OK. Now we just need to figure out what the constraints look like. Right? We've got the signs of the variables. We've got the objective function. Now we just have to figure out what the constraints look like. So how do I figure out what the constraints are? Well, I have to go back and look at the matrix, right? And how do what do I look at in order to read a constraint out of the matrix? What do the constraints correspond to in this matrix? Yes? Columns. So I need to look down a particular column in order to understand a constraint in the primal, right? So when I look at the column corresponding to vertex I, right, what am I going to see? Remember, we figured out what's in this matrix by thinking in rows. Now we have to think in columns in order to understand what constraints come out in the primal. So what am I going to see? Right? Well, obviously, I'm going to see zeros and ones and minus ones, but which ones? Yes?
So you'll see for every node which edges are going into and out of that node.
Exactly. If I'm looking at vertex I, right, as we discussed before, I'm going to see a +1 where there is an edge going into, for any edge which is going into vertex I. And I'm going to see a -1 for every edge which is going out of vertex I, right? So what I can say is that the sum over j's of, let's see, do I want to write it this way? This is not completely consistent with the notation I've been using so far, but I think it's the easiest way to understand what I'm talking about, right? If there is an edge going in to vertex I, right, then that gets multiplied with a positive coefficient on y, right? If there is an edge going out of vertex I, then I need a -1, so that means that I subtract that variable instead, right? So this is what the constraint looks like. Now, what does the bound look like? So there's two separate questions. What is the quantity of the bound? And then there's what is the direction of the bound? Right, so
We will look at the objective of dual, and when we look at the objective of dual, we see that dt has 1. So the one corresponding to the terminal node should be 1. The one corresponding to source node should be -1, and the other one should be...
exactly. So just like we went from the bounds in the dual to the coefficients of the objective in the primal, we also go from the coefficients of the objective in the dual to the bounds in the primal. So what we're going to see over here is a +1 if I is equal to t, a -1 if I is equal to s, and 0 otherwise as our bounds. Yes? I just read that right off of the objective of the dual. Okay. So the final question is, what is the direction of the constraint? Do we want equality or upper bounds or lower bounds? Yes? We want equality. Why? Exactly. We put no constraints on the DI here. Unrestricted variables correspond to equality constraints. So now we're done, right? We just mechanically constructed the dual. It required no insight or creativity at all. Right? We just followed the cookbook. Okay? But here's what's really interesting about this. Taking a dual is an entirely mechanical process, but it creates insight. It gives you a different way of looking at the problem. Okay? So we know from strong duality that this is also a formulation of the shortest paths problem. Right? But it's a completely different formulation. And if we look at it, we can understand something about what it means. Okay? So what do we have here, right? I've got these values on the edges, right? And sort of the sum coming into a vertex has to equal the sum coming out of a vertex, unless that vertex is S or T, right? What kind of problem formulation is that? Yes? It's a flow, right? We can think of the Yij as the value of the flow on edge Ij. Okay. And so what are these constraints? They're the balance constraints, right? That the amount of flow, the net flow through any arriving at a vertex has to be 0, unless the vertex is S or T. Now, this is not a max flow problem, because what is our constraint on the flow from S or T? 1. 1 unit of flow. And what is the objective function? Yeah? Exactly. So what our dual is saying is that another way to formulate the shortest path problem as a linear program is to ask, what is the cheapest way to send a unit of flow from S to T? Right? And the dualization process figured that out completely mechanically. Right? We didn't have to have that insight. And so if you hadn't been previously thinking about shortest paths that way, this would tell you, here is another perspective on shortest paths. Okay? And so this is one of the real values of duals, is that they give you more insight into your problem. Yes?
Yes, this is really beautiful, but if we formulate the shortest path dual in another way, say we put more constraints on these d variables, which
Yep.
are non-negative,
Yep.
and that will definitely ruin the private problem.
Well, it will change it, but it will not ruin it, right? If you make a change to this linear program, under which it is still the shortest paths problem, then the other LP will also still be the shortest paths problem. So yes, we could constrain all of the variables to be non-negative, right? We argued before that shifting doesn't matter, so we can certainly constrain all the variables to be non-negative. If we do that, what happens to this linear program? Yes?
This time it will be greater than or equal to, and the minimization objective will set them to as equal to 1.
Exactly. If we constrain the variables over here, it will loosen the constraints on, it will loosen these constraints so that they will be upper bounds, or they'll be lower bounds, right? Which is basically requiring that the amount of flow leaving be at least the amount of flow entering, or the other way around, right? But the point is that having an imbalance only increases your cost. Like, you still have to send a unit of flow, and so if you have excess anywhere, you're just paying more and you're not accomplishing anything, right? So that loosened constraint over here does not actually give you any better value. So this will still be solving the shortest path problem. Okay? All right. Any questions about that before I take us through another example? It's not a tremendously different example because we've already encountered flow, but let's look at the max flow problem. All right, so in order to make this LP more elegant, instead of formulating it as a traditional max flow, I'm going to turn it into a circulation problem. Okay? So I'm going to add an edge from T to S with infinite capacity. And I'm simply going to ask to maximize the flow on it. Okay? So a circulation that maximizes the flow from T to S is just an ST max flow, right? But it'll just make the LP a little bit more elegant. Okay? So we're doing a maximization now. Sorry, this is again going to be the dual because I'm starting with the maximization problem. Okay. So I'm going to want to take some quantity, which is the maximum of the flow from T to S. Right? With what constraints? Well, we've already seen them in our previous dual example. We want the sum over all other vertices W of xVW minus xWV should be equal to 0, right? This is everywhere because it's a circulation. Right? We also are going to want the capacity constraints. that XUV, that XVW is less than or equal to U sub VW. And also, we want flows to be non-negative, just to keep our intuitions happy. Yes? So this is an LP for the max flow problem. So let's ask again what the primal looks like. Okay. So the first question that you ask when you're doing your dual process is to ask, what are the variables that I'm going to talk about? So how do I figure out what variables are going to appear in the primal? What do they correspond to? Constraints of the dual in this case, right? So you'll notice that I have two different kinds of constraints, right? I have the balance constraints and the capacity constraints. And so it's natural for me to define two different types of variables in the primal linear program, right? So what I can do is I can define a variable z sub v per balance constraint, and a variable y sub e per capacity constraint. Yes? Okay, now I know what the variables are. What can I say about the objective? Right? The objective is generally pretty easy to read off once I've decided what the variables are. Where do I find the coefficients of the objective function? Yes?
Constraints.
What part of the constraints? The bounding values for the constraints, right? So here I have zeros and UVWs. Those become the coefficients of the objective. Now, the zeros multiply which variables? The ZVs, right? Whereas the UVWs multiply the YVWs. So the objective is sum of UVW, YVW. Yes? And since it's a dual of a maximization problem, here we have a minimization problem. Okay. Now, we can also say, relatively straightforwardly, what kinds of variables we have, right? Are the ZVs and YEs, what sort of sign constraints do they have? Yes?
YEs are greater than or equal to 0.
Exactly, right? So the ZVs correspond to equality constraints, so they have no restriction. The Y sub E's correspond to upper bound constraints on a maximization problem. So again, they are the natural kind of constraints. And that means that the Y sub E's are required to be non-negative. Okay. So the last sort of messy hard part is transposing the constraint matrix, so to speak, right? So these constraints and these constraints define rows of the constraint matrix, right? But we have to understand the columns of the constraint matrix in order to read off the constraints of the dual linear program, right? So what we're going to have for the primal, for what I'm calling the dual over here, is in a particular row, we're going to have a whole bunch of plus and minus ones. Right? To sum up all of the incoming edges and subtract off all of the outgoing edges. Sorry, I said that backwards. To add up all of the outgoing edges and subtract off all of the incoming edges from V, right? So we're going to have a bunch of constraints like that. And then underneath it, what matrix shape are we going to get here? Yeah? Yeah, right? So here, this is a very simple constraint structure. Each variable is bounded on its own. So this is just going to be the identity matrix. Okay. So what happens when we transpose that, right? Now we need to look down a particular column of this matrix, right? How are the columns indexed? We have a constraint, over here we have a constraint per what? Yeah?
We have one constraint per one of the edges of the original one.
Correct. We have a constraint per edge, right? Right, because these variables are edge variables, right? So when we take the dual, we get edge constraints. So what non-zero coefficients are we going to see for a particular edge? Well, what created the non-zero coefficients, right? We had plus ones and minus ones in a row when you had an edge coming into a vertex or going out of a vertex. So when we look in the column, where do we see a plus one or a minus one? Yeah?
The vertex, the edge is entering and leaving.
Exactly. We're going to have exactly two non-zeros in this part, corresponding to the vertex that the edge is entering and the vertex that the edge is leaving. Okay? This is just the reverse of the dualization that we did for shortest paths. Right? So what that means is that we're going to see over here a ZV minus ZW, right? Okay, because those are the variables that correspond to these rows, right? But notice we also have the identity matrix down here. What does that add to our constraint? Yeah? Exactly. And it adds it with a plus one coefficient, right? And now, what are the constraints on this formula? Yeah?
Or that be non-negative duals, so that be non-negative.
Or, sorry, it's very non-negative variables that you don't say whether a constraint is non-negative or not, but you have to say whether it's an upper bound or a lower bound. Exactly, right? Again, our variables are non-negative, so our constraints are in the natural direction. This is a minimization problem, so you're going to see lower bounding constraints. And what are the bounding values? Where do we find them? Yes?
Other than TS, H corresponding to TS, they are all zeros. TS corresponds to 1.
Exactly. We find the bounding values by looking at the objective function in the dual. The objective function in the dual has exactly one non-zero coefficient, right? So all the bounds here are going to be 0, except, actually, let me write it this way. In the one special case of, sorry, this is VW, not WV. in the one special case of VW equals ST, you get a 1 and a 0 otherwise. And finally, as we said, the y's are non-negative. Okay. So we now have, by strong duality, a completely different valid formulation of the Maxwell problem. The question is, can we assign it some intuitive sense? Okay. So what are we trying to do here? We're putting a value on each edge, a YVW, and then we're multiplying it by a capacity. Okay. And then we have these constraints. Does this constraint look familiar? ZV, you know, something that involves a ZV minus a ZW plus a YVW. Yes? It feels like reduced costs. And what were those reduced costs related to? Shortest paths, right? So this looks like a kind of a triangle inequality constraint, right? So we can think of the ZVs as distances from S, say. Right? And we might want to rewrite this to say that ZV is less than or equal to, let's see, did I want to put this in the, sorry, hang on one second. Yeah, that ZW is less than or equal to ZV plus YVW, right? So this is just saying that our Z's, our distances, satisfy triangle inequalities, right? Using these lengths YVW, which are now the variables. So we get to pick the lengths, okay? We pick lengths, and they determine distances. And what are our constraints on those distances? Well, for the most part, they're just triangle inequality constraints. But there's also this constraint that says what? Yeah?
I was going to say, like, separate, it's kind of like nin cut, except in nin cut, you're assigning like everything either 0 or 1.
Mm-hmm.
That's the two sets. But then here,
Very good. Very good. So yes, we're heading towards a cut formulation, right? Because what this is saying is you have to pick distances, you have to pick lengths that separate S and T at distance of at least 1. Right? What is it that you're trying to minimize? The sum of length of edge times capacity of edge. So you can kind of think of that as a volume of the, right? If you imagine that the capacities represent the cross-sectional area of a pipe that determines how much can flow through it, right? Then when you set a length to that pipe, what you're doing is you're establishing how much volume that pipe occupies. And what we are being told to do is minimize the volume of that network, subject to forcing S and T apart from each other. Okay. Now, as you just pointed out, one way to solve this linear program is by making a cut. Right? If I find a cut of a certain value, how can I use that cut in order to give a solution to this linear program? Maybe not an optimal one, but what should you do? Yes?
So the distance of every node on the left side of the path is 0, and all the distances on the right side of the path is 1, and then
Exactly. Right? So, or to reverse it, if I put 1 on all the cut edges, right, if I set YVW equal 1 on every cut edge, and then compute distances, then all the distances will be 0 on the S side and 1 on the T side, because the only way to get to the T side is by crossing the cut. Right? So every cut gives you a solution whose value is the capacity of the cut. And so weak duality tells us that, right, from that we get that any cut is an upper bound on the value of the maximum flow. Right? Because any cut gives a solution to the primal linear program, which is, by weak duality, an upper bound on the value of the dual linear program. So max flow is less than or equal to min cut. Now, we actually know more. We know that max flow is equal to min cut. But we don't get that automatically from strong duality. Because the worry is, maybe there's a solution to this primal that is not a cut, but that is better than all the cuts. Right? So I'm going to let you worry about that for a little bit while we take a break. Okay? And then we will come back and address that. Let's resume. So I think this lecture might win for smallest number of boards. Let's see. So in order to think about max flow min cut, I need to draw in another idea that we've already talked about, which is complementary slackness. This is something that came out in min-cost flow, and it turns out to be very important in general linear programming. And it's easiest to talk about, again, going back to standard form linear programs. But in general, okay, given feasible solutions x and y to the primal and dual, we define what's called the duality gap as the difference between the two objective functions. Okay? The duality gap measures how far away we are from, how far the solutions are from each other, and we know that the optimum is somewhere in between. And that means that if they're that close to each other, they're also both that close to the optimum. So if the duality gap is small, you know that both of your solutions are close to optimal. Right? By weak duality, we know that this duality gap is always non-negative, okay, because the minimization solution is always bigger than the maximization solution. We also know by strong duality that there is a solution where the duality gap is 0. So now let us rewrite our linear program a little bit. So if we start with a standard form, where we're minimizing, and we have the canonical dual, we want to maximize YB such that YA is less than or equal to C. I can transform the canonical linear program into a more standard linear program by adding slack variables. Instead of saying YA is less than or equal to C, what I'm going to say is that I want YA plus S to be equal to C and S greater than or equal to 0. And so all I've done is I've introduced these slack variables that we've talked about before. Okay. Sorry, I shouldn't be so sloppy. Slack variables. So I introduced these slack variables. And now, if I write out my duality gap, Cx minus Yb, all right, what we've asserted is that so that Ax is equal to B. So this is equal to Cx minus Yax, right? Times, Ax is equal to B. Yes, that's right. So this is equal to C minus Ya times x, right? But C minus Ya is just S. So this is just S times x, right? So it's the product of each variable in the primal with the corresponding slack. It's dotted with the slacks in the dual. Okay, so it's a very simple representation of the duality gap. Okay. But remember that S and X are both constrained to be non-negative. Right? Now, at duality, or at optimality, right, SS is equal to 0. What's the only way that you can have Sx equal to 0 if all of the relevant variables are non-negative? Yes?
Either like S is 0 as the component or like X is 0 as the component.
Exactly. Right? So the only way to get Sx to be equal to 0, since each value is non-negative, is to have each term be equal to 0, right? Because if anything is positive, there's no way to cancel it out. Okay. Of course, this is an if and only if, right? Because if all of the Si, Xi are 0, then the value of Sx is 0, which means the duality gap is 0, which means you're at the optimum. Okay. But what does that mean, that all S's and X's are 0s? What it means is that any time xi is equal to 0, right? Sorry, is not equal to 0, right? If xi is not 0, that requires that si be 0. And what does it mean for a slack to be 0? It means the constraint is tight. Okay? So this is the same complementary slackness concept that we hit in min-cost flow. Okay? At the optimum for a linear program, if you have any non-zero variable in the primal, the corresponding constraint in the dual is going to be tight. And conversely, if you have any non-zero variable in the dual, the corresponding constraint in the primal is going to be tight. Okay. And again, it's an if and only if. At the optimum, complementary slackness holds. And if you have complementary slackness, you are at optimum. Okay. So let's apply this to the max flow linear program. Okay. So we've already started to draw this connection to cuts, but we're not sure they're cuts yet. Right? We have weak duality, but we haven't really understood fully what's going on with strong duality. Okay. So let's consider our optimal y star and z star from the primal linear program that we constructed. Okay. And now is where we invoke a bit of creativity. I'm going to define a set S of vertices to be equal to all the vertices whose distance from S, sorry, do I want to, yeah. Let me point out that, again, we have a shift invariant linear program here. Right? It's only talking about differences between the V's and the W's. So I'm going to say that without loss of generality, Zs is equal to 0. Okay. Or Z star S. And so now I'm going to define a set S, a set of vertices, which of course means that it's a cut, to be all the vertices whose distance from S is strictly less than 1. Okay. So we can immediately say that little s is in the set, its distance is 0, and little t is not in the set because its distance is 1. So we have defined an ST cut. Now, what can we say about this ST cut? Okay. Now we're going to use complementary slackness. So if the edge VW leaves the set S, what does that mean? Well, in particular, what does that mean about the value of y star VW? It's non-zero, right? In order for ZW to, right? If VW leaves S, it means that ZV is less than 1, but ZW is greater than 1, or greater than or equal to 1, right? Which means that v minus zw is negative, which means that yv star has to be non-negative in order to cancel it out, right? Given the greater than or equal to 0 lower bound. Now, if yv star is greater than 0, what does complementary slackness tell us? Yeah? Why?
Because if YVW is greater than 0, but we're at the optimum, then the corresponding slack variable has to be.
Exactly. We have to draw this correspondence. So here we have a variable which is not 0. What complementary slackness tells us is that if you have a non-zero variable, then the corresponding constraint is tight. So what is the corresponding constraint to the variable yvw?
The capacity bound.
It's the capacity bound, right? So our variable ye over here corresponds to a capacity bound in the so-called dual. And because the variable is loose, it means that the capacity constraint is tight. In other words, xvw is equal to uvw. Yes? What if, on the other hand, VW enters S? Let me go over here. Okay. Well, if VW enters S, that means that ZV star is strictly greater than ZW star. Because again, one of them is equal to 1, and the other is less than 1. Okay? We also know that y star VW is greater than or equal to 0, because that's one of the constraints of the linear program. So if we put those together, we find out that ZV star plus y star VW is strictly greater than Z star W. Right? So what is this? What are we looking at here?
A non-tight constraint.
This is a non-tight. This is a loose constraint. What does complementary slackness tell me about loose constraints? Yeah?
Corresponding slack variable must be 0.
Right. Corresponding variable is 0. What is the corresponding variable to this constraint? Yeah?
Well,
It's the variable for the flow on VW. Right? So put these things together, right? If VW is leaving S, then the flow is equal to the capacity. The edge is saturated. If VW is entering S, then the flow on the edge is 0. Okay? So in other words, X star saturates all the exiting edges and empties the entering edges, right? Which means that the value of the flow is at least the capacity, sorry, is equal to the capacity of this cut that we just constructed. So we have, in fact, recovered the maximum in-cut theorem just by applying complementary slackness to the dual. Okay. And so this is the nature of duality. It's this sort of sledgehammer that yields all sorts of powerful results as side effects. Okay. So next time, we'll just take one more dual for kicks. We'll look at min-cost flow. And then I'll spend most of the lecture telling you about how we actually solve linear programs algorithmically. Any final questions? Yes?
How do you know the corresponding variables that
Oh, that just comes straight from the rule for duals, right? If you look at how we constructed the dual, right, there's this direct mapping between the variables of the primal and the constraints of the dual.